Right, hello everyone, and welcome to the SoilWorks presentation for Midas. We're going to be focused today on 2D finite elements versus limit equilibrium analysis of slope stability. My name is Adam Kane and I'm a technical support engineer for Midas, and I'll be taking you through proceedings today. What I want to do first is just do a very quick sound check. We've done a test just before, so we know in office that we can hear it, but we just want some people to raise their hand in the room. So yep, alright, thank you very much. I can see that a couple of you have just raised your hands very quickly there. That's very good of you and very kind. If you want to contact us, if you have any technical difficulties, please phone the number on the screen or just email into UK support and somebody will answer the phone to you. So just go through some of the general housekeeping rules. I know that you can hear me now and you can see my screen. If you want to maximize your screen, just click on the two overlaying boxes up in the top right hand corner of the screen, and from there you'll be able to maximize it. If it does happen to go, your screensaver happens to kick in and your screen goes blank, then please set it to off or wiggle the mouse. So just using the go to webinar box, if you click on the red arrow it will go down to a thin strip. You are able to ask questions throughout and somebody will respond through a text form to answer any of your questions. So in our last webinar we saw the application of the limit equilibrium method and finite element method analysis for stability, pore pressure and coupled problems in geotechnics, with demonstrations in our 2D software SoilWorks. Midas GTS NX is our 3D finite element analysis software for geotechnical and tunnel analysis. Apart from geotechnics, Midas also develops solutions for buildings, bridges and mechanical industries. So just an introduction. Slopes are encountered during construction of embankments or digging out of trenches. Stability of slopes is one of the most common yet challenging aspects in geotechnics. The sequence of images on the screen below graphically show that initially a slope is stable under its own self-weight. Instability is often in the slope arises due to the action of external forces such as horizontal loads, seismic action or the seepage. A slope fails when induced shear stress due to these external loads exceeds the shear strength of the material itself. Choosing accurate material strength parameters is of most important, a very important factor which could determine stability of an engineered slope or any reinforcement requirements. So just the limit equilibrium method determines the global factor of safety for a slope using equilibrium of force and moments of each individual slice. The factor of safety is obtained from statics, as is given as the ratio of resisting to driving forces. If this value is less than 1, then the slope is unstable. So different solution techniques have been proposed, and they mostly differ in what assumptions and formulations are made to solve the slope stability problem through statics. So another major difference comes in the form of how interslice shear forces are handled by the solution techniques. For example, the Morgenstern price method has different functions to define the orientation and location of interslice shear forces. So the half sign means that the interslice shear force is concentrated on the middle of the slice. Slip surfaces could either be the arc type, polygonal type or composite. One of the major drawbacks of the LEM or the limit equilibrium method is that it assumes one constant value of the factor of safety for all the slices. So therefore the LEM analysis does not predict accurate local slice behavior, such as the normal stresses, etc., things like that basically. So for the global equilibrium, all the inconsistencies are smoothened out in the algebraic sum, and hence global factors of safety can be obtained with a good degree of confidence. So just go through some of the reinforcements of the slope stability, depending on the practical issues such as type of project, for example whether it is an excavation or an MES wall, or if there are any adjacent structures such as utility pipes, the type of reinforcement for slope stability could vary. The table shows some of the common types of reinforcements which can be considered in soil works. Anchors can be defined to take actual loads, and which can be pre-stress, and they can also be grouted types of anchors that can be modelled as well. Nails provide resistance to axial and shear directions and have comparatively large sections than anchors, or large cross sections than the anchors. Strip and fabric can be modelled with the input of pull-out strength and frictional behaviour with ground material. Struts or props are the most widely used structural support for temporary excavations in urban areas. Geogrids, the next one, which can be modelled as a tension-only element. Piles can also be used for slope stability due to the shear resistance provided by them, and all these types of structures supports can be modelled for both the limit equilibrium method and the finite element method. So now I'm going to bring the program across and just show you the basic GUI and the limit equilibrium method reinforcement. So this is the GUI and the ribbon technology going along the top. So as you can see, the geometry you can build up. You've also got the equilibrium method and the different methods you can go through just by selecting them. We've also got the different models, load and boundary conditions for reinforcement, and we can also go through all the analysis and design. So just in the works tree here, where it builds up all your information chronologically, you can see some of the ground material properties. So we just go down to the modify and we can just change it. We do have different drop downs and everything too, so you can select the different model type and the elastic ground and everything like that. And we've also got a database where you can select all of the different types of materials. So as you can see, we've got a comprehensive list of materials there. Not a black box, you can add your own. So just to look at the structural properties, and here we have the geogrid. So you can build it up and you can actually put all the general parameters and the reinforcement loads. So as you can see, we put it in tension only. We've also got different types of element type as well. As you see what I was just previously explaining in the slide from the table, where you've got piles and everything like that. So just go back into the presentation. So as mentioned before, different types of LEM methods exist, differing in how they solve the problem of equilibrium of slices by statics. You can see the pros and cons of each method in the table. So Bishop's method is mostly widely used for slope stability analysis and is well suited for clays, as cohesive materials often go through rotational failure of mass volume about a point of rotation. For more complex problems involving highly heterogeneous ground with layers of different materials between adjacent layers, and where the interslice shear force is expected to vary, one can use Morgenstern-Price method using variable functions for modelling interslice shear forces. So just to go back into the software, and I'll show you different analysis options for the limit equilibrium method. So here we have the slope stability problem, and we've got the geogrids that are making up the different stages. As you can see, it's built up, so you've got different levels of geogrids going all the way up from the bottom of the construction. It's in two different stages. You can see the different surfaces, and you can select them from the table. And you can see the water profile going up from the actual onto the ground there, the hydrostatic pressure. We can look at the different surfaces, and we can also look at the factor of safety as well, and the boundary conditions, and the arc failure surface, as you can see, going down through there. And we've got a multitude of arc fail surfaces as well that we've generated. So just going to modify the analysis cases. So as you can see, you can select a multitude of different analysis cases, and you can also pick the splice you wish to as well. So the analysis method, and the bishop, and the jambu, and the Morgenstern price. So we can use a different we can use a define, and we can also do the using functions for the trapezoidal and also the Morgenstern as well. So just to go through that and just go back from that, so just show you different analysis cases. That'll take you back into the presentation itself, or look at the post-processing. So just going into the post-processing, then we can see the factors of safety, and you can see the best factor of safety of 1.3. And we can also look at different splices as well and how we can interpret those. So as you can see, the free slice and the bishop method, and the free body diagrams that are generated, and we can flick between left to right, and you can see all the different values that have been created. So just go back into the presentation. So just go through the finite element method. Due to the shortcomings in the limit equilibrium method for modelling the actual failure mechanism of satisfy kinematics during slope failure, continuum-based methods were developed, such as finite element methods, finite differences, boundary element method, and discrete element methods. Among these methods, finite element methods are most widely used to solve slope stability problems, assuming that the material is continuous. The finite element method gives more precise results, as the analysis maintain force equilibrium, displacement compatibility at each node, constitutive equations to model linear elastic, non-linear elastic, and elastoplastic material behavior, and the boundary conditions. So the finite element method requires iterative analysis, so computationality. They're a little more expensive than the limit equilibrium method in terms of definition of model through mesh and analysis runtime, but the finite element methods are of two different types. So the strength reduction method, or C-phi reduction, the stress analysis method, which is a combination of the limit equilibrium method and the finite element method, and hence it is more advantageous. So just go through the strength reduction method, which was first proposed by Singwicki. In this method, the shear strength parameters, cohesion, and internal friction angle are gradually reduced until divergence in the solution with respect to the convergence criteria, such as bases of displacement or force or strain energy that occur. At that point, the slope is said to have failed. The final strength parameters are obtained by dividing the initial values by the factor of safety obtained from the analysis. So the strength reduction method and the finite element method analysis generally is sensitive to the dilation which would happen when the ground material is sheared. When the dilation is equal to initial friction angle, the analysis would run faster because of associated plasticity, but you might see higher magnitude of deformation, whereas if they are not equal, the analysis runtime would be higher, but the results would be more credible, representative of actual deformation within the ground. So the strength reduction method can model situations including effects of different types of reinforcement, surcharge loads, and groundwater conditions. As it was said in the previous webinar, input of elasticity modulus will also affect how the deformations will occur within the soil, and if reinforcements are present, then their relative ratio would determine the development of strains and displacements as the material shears. So just to go back into the software and show you the strength reduction method and the maximum equivalent strain. So as you can see, it's all completely meshed and the slope's been meshed. And just to take you in the post-processing, show you the strength reduction method and the maximum factor of safety there, or the factor of safety, sorry, which is automatically calculated. So just take you to the maximum shear strain, and as you can see, that is the failure plane that's been created, and it's the slope failure plane has been developed. And now I'm going to show you the seepage slope coupled analysis. And first we'll just go through the seepage model with the actual mesh itself, so just to bring that one over now. So bring the model over, just going to take you over into the seepage coupled analysis model. And here you have it already meshed and everything, so all the actual layers have been created for the geometry and the ground layers as well. So here's the different mesh sets with the weathered rock and the soft rock and everything like that. So got some of the properties and weathered soil. So we just take through the modified, exactly the same thing with the different parameters to select and the different database, and also the unsaturated property type, which we can manipulate and change. So you can see you've got the soft rock there and weathered rock, and you can actually change the parameters, save them, do what you want. So just go through the different boundary conditions and the initial water level, as you can see the groundwater there, and going up through. And then you've got the rainfall intensity, so as the rain falls down the top of the slope and permeates down or flows down towards the bottom of the excavation or the bottom of the slope. Then you've got the actual review, which is the determination of Finite surface. And then we've also got the different construction stages, so just to go through and modify one of them, just to show the construction stage, you can see the transient state for the seepage analysis, and we've also got the transient state analysis with the time steps. So just to define the construction stage analysis. Here, this is where you can just drag and drop the different cases. So this is construction stage 1, and you've got the initial water level. And you've got construction stage 2, which is the rainfall intensity and also the review. So just to look at the post-processing, and you can look at it through the deformations in the seepage flow. So here we have the phreatic line in construction stage 1, and we can also see the phreatic line in the construction stage 2, and it's being raised, as you can see, by the blue line indicated, and obviously it's increasing as we go through the different construction stages. And there you see it once again once the rainfall has occurred and everything like that. So now we've obtained the seepage analysis. So as the ground's becoming more saturated, as more and more rainfall falls through the different days, so obviously we've got day 1, day 2, the factor of safety is decreasing. So as you see by day 2, then it's actually decreasing by a factor of 1, and then it goes down even further by day 3. So here we have the arc failure surface that's been generated, and your splices there as well, so we can look through those again, and the different free body diagrams. So we can just close that, and there's all the results, but we can look at those through the different structure stages. So just to conclude, that is the coupled analysis of the seepage analysis and the slope analysis in one within SoilWorks. And now we're going to look at the stress analysis method. So the stress analysis method offers the simplicity of the limit equilibrium method and the accuracy of the finite element method in one method. Effects such as ground stress history, deformation and groundwater flow, seepage can be considered through the finite element method. For the strength reduction method and the stress analysis method, it is recommended to mesh the geometry with higher order or quadratic elements. So now I'm going to look at the consolidation and the slope coupled analysis and the effects of the ground improvement due to consolidation and its impact on the slope, stability, which can be reflected with a coupled analysis. So now just bringing over the ground model now. So as you can see, this is another embankment, and we've got the different ground layers and different material layers as they're built up. So we've just got the upper clay, and we can also select that and just manipulate it and show you. Just look at the different ones. So as you see, all the different ground layers going down through and the different drainage types. So which the drains are improved. The drains are implemented to improve the consolidation of the soil as the different ground builds up, and we've got a selection of different drainage types that you can select. So just go through different analysis cases and different simulation of construction stages. So embankment 1, so as you can see the first part being added, and the second and the third, and as these layers are all added, then the consolidation of the soil underneath and the material properties change. So I'm just going to show you the material properties as they change going through. So just look at the increase in strength through the different stages. So as you can see, that soil is actually increasing in strength through the different construction stages, going through to embankment 3, which you can see by the columns in the bottom of the table there. So just to create the slope model and bring it over. So just by clicking here, this will automatically create the slope module. In effect, you don't have to create two separate models. So just to show you the slope module, to take you straight over. We've got the different analysis cases through the construction stages, the consolidation of the soil and the arc failure surfaces, with all your factors of safety and everything like that. So just to go into the post-processing and show you the factors of safety, and you can also see them graphically with the failure planes and also, well, the arc failures and also the splices. So due to the consolidation of the soil, it will go through the deep-seated failure of the clays. So that is the deep-seated failure, and I'll be going back into the presentation to show you a few more slides. So just the different numerical approaches. The main difference between the limit equilibrium method and the continuum based method are highlighted. The limit equilibrium solves a problem using statics by dividing slope into a multitude of different slices, where continuum based methods involve more detailed behaviour using FE, FD, BEM or DEM methods. Constitutive equations for ground and structure and elastic plastic behaviour are all included. So the LEM only gives results for the factor of safety and force diagrams for each splice, but continuum based methods give additional results for deformed shaped stresses and strains in the ground. The limit equilibrium analysis model is easy to set up, but it does not accurately account for variation in the ground properties, the stiffness from the structural elements, and the overall kinematic of slope failure. The following quote from Will and Ma highlights the problem. So the limit equilibrium method just gives an estimate of the factor of safety with no information or deformation of the slope, but in numerical analysis the failure surface can evolve during the calculations in a way that is representative of the natural evolution of the physical failure plane in the slope. So just some tips. The main problem in slope stability analysis is how it's choose appropriate shear strength parameters and to account for the pore pressures. This table highlights common design situations and how to choose these parameters accordingly. During and end of construction, drained conditions and drain strength is used for free draining soils and for low permeable soils. Undrained strength is used and total stress analysis is performed. Pore pressures could be hydrostatic or derived from steady state analysis for free draining soils, whereas for impermeable soils they are neglected or taken as zero. Steady state seepage is in an embankment, be it high or low permeable soil. Under steady state, drained material strength is used. Pore pressures could be hydrostatic or derived from steady state seepage by FE or FD or flow nets. So for sudden drawdowns, it is a bit more complex. For free draining soils, drain shear strength and pore pressures are used before and after drawdown, but for low permeable soils it's a 3-stage approach. So for strength, first use drained shear strength, drained shear strength. In second, use undrained shear strength related to consolidation pressure, and in the third, choose whichever option offers lower factors of safety. The pore pressures accordingly can either be used for steady state seepage or set to zero for representative analysis. So just some more tips. The shear strength can be modelled with a linear, mohiculum, envelope or non-linear. The actual ground conditions are much better represented by non-linear shear strength envelopes, and for the total stress analysis in saturated clays, always keep internal friction angle to zero. It is positive only in the case of partial saturated clays. It's recommended to use total unit weight rather than using submerged unit weight. Using submerged unit weight doesn't offer any significant advantage. So in soft clays and loose sands, which have ductile stress strain behaviour and hence peak strength, can be used to represent the shear strength in the analysis, whereas the stiff clays and dense sands have brittle stress strain behaviour, and in this case residual shear strength should be used. Use of cohesion interpret for mohiculum yield surface means that the ground would have a certain amount of tension capacity. This should be manually controlled either by defining the tension capacity as zero in the finite element method analysis or including a tension crack. The tension crack develops near the crest of the slope as shown in the image, and the depth of the crack should be chosen such that it eliminates tension but not compression stresses. So just in summary, for the slope stability analysis, you can have different geometries and different ground data that can be incorporated. You can also do the different external loads and the pore water pressures for different construction stages. For the analysis method, you can do the limit equilibrium method and finite element method, along with the strength reduction method and the stress analysis method. For the limit equilibrium method, which is easy to implement, you've got little analysis time, but it requires assumptions for the failure surfaces to calculate them. And for the finite element method, offers results for ground deformations and the factors of safety without assumptions for failure surfaces, but intensive in terms of mesh generation and analysis time. The strength analysis method combines the benefits of the finite element method and the limit equilibrium method. So as you can see from this, the illustrated diagrams on the screen, that you can combine all three and you only have to create one model in SoilWorks. So thank you for tuning into this webinar today. Just to let you know, our content is uploaded to YouTube, and you can click into any of our channels and learn more about the Midas products, and also to more learning about geotechnics and structural and also bridges. So my name's been Adam Kane, and thank you for coming along today. If you do wish to contact us, then all our details are on the screen. If you want a bespoke demonstration or a validation copy of the software, just please come in and we'll be able to provide you with that.